my goodness. Jams. All right. I'm so happy to be back in Taipei. Oh my goodness. Okay, so this talk, you may have seen parts of it before. Honestly, it's kind of like an evergreen talk, and I kind of need to set this context over and over again because it is so important. And honestly, I've been giving this talk, I feel like, for 9 years trying to scale Ethereum. It's been an absolute journey, but we are getting so close. We're so close to scaling Ethereum finally. So anyway, how are we scaling Ethereum? We're scaling it with the Superchain. And I want to leave time for questions. And so I'm going to set up my phone with a timer so that I don't run out of time, because I'm definitely going to. We're absolutely not going to cover everything that I have here. But let's get in. All right, so talked about the Superchain many a time. We are going to get into the weeds. It's no fun allowed. Let's do this, Leroy Jenkins. Okay, so Superchain to the rescue. This is, the statement, blockchain is insufficient for the web. Why? Well, meet congestion. Congestion is really our bane, the bane of my existence. I will say that right now. We have had high fees on L1, high fees on L2. It is over and over again. This is the challenge. So blockchains do not scale, right? Look at all this. I'm not spending multiple dollars to send out a tweet. Now, notably, I want to actually give a little rant here before I even talk about how this is not new information. I think we really underappreciate how important it is to lower the price of transactions. Because, okay, it's one thing to have a 1 cent per transaction. At that scale, you may even still need to, have a wallet and have, a couple bucks of ETH and kind of get through the day. But when we get down to 0.00 cents, we start approaching a kind of limit of, transaction cost that kind of resembles the cost of quote unquote transacting on the traditional web. And that means that users don't need to worry about paying gas, period, because it's so cheap. You might as well just, pay the gas for your users, or, maybe you make an account and you get a free gas allocation every month, or maybe you various ways to pay to kind of get rid of the gas paying experience. And so that brings the blockchain out of the purview of the end user, and means that they can focus on actually doing the thing that they came here to do and not have to worry about wallets and all this kind of stuff. I really think that we're not quite there yet, but we're starting to see a kind of perfect storm of things like embedded wallets combined with the lower fees on L2s with 444, and all of these things come together to provide a user experience that's actually acceptable to onboard large numbers of users. Now, we're not there yet, to be super clear. The infrastructure is not there yet. The applications are not there yet. But we're getting that tiny little taste of what it could be to transact with a Web3 application and have it actually be a better experience than a Web2 application. So anyway, I just wanted to pause here because $13 is one thing. Even 1 cent is one thing, but 0.000, some cents, whole different story, whole different ball game. All right, I told myself I was going to blaze through this presentation. I'm three slides in and 3 minutes in. Okay, anyway, back to the regularly scheduled programming. This is not new information. The first response to the Bitcoin white paper was, hey, this thing doesn't scale. I love your idea. It doesn't really work, though. And you know what? They were right. I mean, Bitcoin's done great things, and Ethereum's done great things, but we're not there yet. So it's been, many, many years, and we're still not fully there. But imagine if we were. Imagine if we were. And we could use, we weren't just trading dog coins, and we were providing real value to users, and everyone was happy. And we created a developer platform that's serverless and composable and free to use and all these kinds of things. Oh man, I really want to be an application developer and not have to worry about hosting and infrastructure costs, because we've decoupled it sufficiently so that I can just define the logic of my application, and then users can go bring their own gas and, play with it. Like there's so many things that we're really going to get from building out this infrastructure. We're so close. Oh my God, look, the internet currently is a lockdown prison, dying, and it's going to become beautiful and vibrant and all this kind of stuff while the ocean goes the other direction. Anyway, no, okay, we'll fix that. We'll fix that some other day. We will be able to build things like Twitter and world global scale applications. Okay, how are we going to do this? How are we going to have this amazing world? Well, it's because of years upon years of research, toil, and incredible people joining the industry like y'all. This has been a massive industry-wide effort, from the roll-up-centric future, all these kinds of things. We're coming up with the abstractions, the concepts that will allow us to go from being a, monolithic, slow, hard-to-scale system to a modular, well-run system. And how do you do this? You build the abstractions so that we can all work on this problem together and solve it in small chunks and then compose those chunks into one big, glorious solution. I love this quote. Things that are beautifully done, like the web, the web stack, the networking stack, normally come with really well thought out abstraction layers. So we're getting there. And thanks to all these amazing people, it's coming into clear vision. Congestion, meet the Superchain. Let's go. All right. We're getting there. Anyway, scaling. Okay, so now some fundamentals, just like real quick. What is the Superchain, right? Scaling requires more than one chain. Why is that? Well, you got this node, it's fine, things are chugging along, but then you start increasing the block size until the blocks are so big that it causes a black hole and your computer explodes. So you can't just increase the size of the blocks. You need to do more. So you need more than one chain. But the problem is that multi-chain designs are often insufficient as well, because oftentimes they each come with their own security risk, own validator set, or deploying the chains is super expensive, tons of issues. So we need a kind of system where the chains are commoditized. It's trivial to spin up a new one. You don't need to sync all of them at the same time, and that is the Superchain. It's not monochain, it's not multi-chain, it's the Superchain. All right, so, concept, many different chains, shared security model, shared message passing. And, as we standardize the OP chains, we can get superpowers. Okay, so governing the standard, I'm actually going to breeze through this section, but the TLDR is that, optimism governance is governing the standard, and they're all, all the different chains are on shared security. You can transact between all of them. Don't need to worry about where the tokens came from, because you can trust that all of the proofs will have checked out. Universal tooling so that I can use my application frameworks on one chain or many of the chains. I can also all the shared block explorers and debuggers, and in fact I can even do things like kind of abstract away and start composing many different chains and deploy my application to all of these different chains. Like, who likes having to deploy your smart contract on 30 different chains just to get it working on Polygon or OP mainnet or whatever? It's a pain. I'd much rather have one thing that I can use, and then boom, it's deployed everywhere. So, at least for the standardized chains, we can do this and start building orchestration software for applications, kind of like the Kubernetes, but it's Supernetes. So anyway, and cooperative innovation, right? We're all working together on the shared standard, and we can contribute back upstream. Remember to upstream your changes. It's incredibly important, and that is the beauty of open source. And guess what? With RetroPGF, retroactive public goods funding, you'll get rewarded as well for your contributions. So we can create this virtuous cycle and fund open source software. All right, so we're making public goods sustainable and decentralized. Okay, so that's where we're headed. Windows XP. I don't know. I love Windows XP. Okay, Superchain derivation. So here I'm going to go through two of the concepts because we don't have a lot of time, and I've already burned through a majority of the time that I was planning to take. So the two concepts I'm going to go through today are derivation and cross-chain message passing / interoperability. So these are the two most fundamental, I would say. So derivation. What is derivation? Derivation is the process by which you generate the layer 2 chain from the layer 1 data. What does this mean? This is basically how all the rollups work, and absolutely how all the OP stack rollups work. So we got Ethereum, we derive OP mainnet, or maybe red chain, let's call it red chain. And Alice wants to send a transaction. She sends it over to Ethereum L1, maybe deposit, and then boom, the derivation function is called, and we derive the red chain. So this is really saying that Ethereum defines where all of the transactions and all the ordering, and then we derive what the chain is through that data. All right, so then progress along, and Alice, instead of submitting it directly, submits the transaction to a sequencer. Sequencer kind of relays it on her behalf, and boom, the derivation function kicks in again, and now we have got that transaction. So pretty simple, not too bad. Let's just test our intuitions a bit. Very important. Myth, the sequencer can forge transactions. All right, we'll see. Let's see. So Alice sends the sequencer a signed transaction. Is the sequencer going to be able to forge it? Well, let's see. So sequencer changes the recipient to themselves. They're like, Alice, you thought you were sending to Bob. Nope, you're sending to me now. All right, so now the transaction has an invalid signature. Okay, so that's why it's red. It's an invalid signature. Now, when I call the derivation function, what happens to that transaction? Well, I check the signature of that transaction. I'm like, that does not check out. That transaction is some garbage. And I throw it away, and it does not ever get included in the red chain. What does that mean? Well, that means that myth busted. The sequencer cannot forge transactions because all of the transaction data is posted to L1, and everyone who wants to derive the L2 chain can detect that there was something wrong and throw away the transaction that was forged by the sequencer. So, important concept, sequencer cannot forge transactions. Now, let's talk about, can I connect that to the superchain? Well, this is the derivation function for red chain, but the derivation function changes depending on what chain you are deriving. So blue chain might have a different derivation function. Instead of reading all of the transactions submitted by the OP mainnet sequencer, maybe it's reading all the transactions submitted by the base sequencer or the Zora sequencer. And so we've got blue and purple chain, all the different sequencers submitting their respective transactions. And Alice can choose to derive whichever chain she wants. She syncs a node. She wants to sync the red chain node. Boom, she syncs the red chain node. She wants to sync the blue chain node. Boom, she syncs the blue chain node. So this is actually why L2 scales, right? We're taking this one big list of data, but we're deriving different chains from it. And that means that Alice can run each chain in a different computer, parallelize it. She can choose to not run some of the chains. All of these things, this allows us to get around that bottleneck I mentioned before, where the blocks got too big and Alice's computer exploded because there was too much to do. So that's how we kind of get rid of it. But that's like normal, that's status quo. But let's turn it into a superchain. Let's derive infinite chains. Okay, so instead of defining the derivation function as just the L1 and having a special one for every chain, we can actually define the derivation function as having two inputs. One, the chain configuration, and two, the L1 chain. So that means that based on your config, you now have a different chain. And so however many configs you have, we have different L2 chains. All right, so this gives us access to a practically infinite number of chains. And of course, standard bridges and standard addresses are important. So, pink config, we get that chain, blue config, green config, all the configs, right? That's kind of how it is. And so you can kind of think of it as like a kaleidoscope. You're like looking into the kaleidoscope and you're like, whoa, wow, so many chains. Okay, anyway, that was the super. Sorry, that was that. That's how we derive as many chains as we want to derive. So that kind of gives us infinite compute. Now, notably in this talk, I'm not going to tell you about how we get infinite data, but if you notice, there's a bottleneck on Ethereum L1 with data. We solved that with 4for4 and Alt DA, but, we only have so much time. We're only going to solve some of the problems today. So cross-chain messaging. Okay, so these chains, they're all independent, but how do we solve them communicating with each other? Because it's not going to be super useful if you can't bridge between them or you can't deploy applications that share state between different chains. So let's talk about the fundamentals. Alice and Bob, they want to send some messages to each other. Alice writes a message. She has a to and a message and a proof. Mo, the mail person, grabs the message and brings it to Bob. Okay, so that is, that's messaging. pretty simple in the physical world. Well, what if I told you that they were chains? They were actually chains all along. So Mo, the mail person, is actually really migrating their tokens, sends a transaction to the Alice chain. The Alice chain then emits an event, for example, and then Mo takes that event and all of the proof data and ferries that along to the Bob chain. Bob chain verifies the to, message, and proof and executes the transaction. So that is essentially, that's the core concept of cross-chain messaging. Pretty simple. That's the interoperability stuff, no problem. So, they can talk to each other. Now, it's easy to do the to in the message. That's just information in the message. The proof is really hard. Proof is annoying. Oh my God, we've been working on proofs for years. So how do we verify the authenticity of a message while preserving decentralization, crypto economic, security, etc.? Well, let's actually just go over the fundamentals around how the proof works. Well, the way the proof works is actually the same as the derivation that I was talking about before. That's why I provided that context, because it is actually very useful context. So we're trying to verify a message of red chain on the blue chain. Now, the blue chain knows the red chain configuration and has access to the Ethereum L1 data. They have the access to the latest block hash, for example. And so the blue chain actually knows how to derive the red chain from all of the data that it has access to locally. So the blue chain can actually run that derivation process that we saw and verify the authenticity of the message. Now, you might notice a problem. If I say that that is the only way that the blue chain can verify the message, then they're going to all the chains are going to fully verify each other. It'll kind of collapse into basically a single mega chain. So this is why proof systems, they take a bunch of data that it takes to verify and basically compress it into a much smaller amount of data, right? ZK proofs turn a linear-sized amount of data into a logarithmically sized verification problem. So, different types of proofs, they all serve that similar purpose. All right, so this is a little bit, I'm sorry, it's a good thing. It's some new slides, but there's a bad thing, it's less pretty and less beautiful. So we're gonna change gears into some more work in progress slides, but we can appreciate this very beautiful little gerbils or hamsters. All right, so I'm going to talk a little bit more in the weeds than before about some of the interop specs, which you can look at. You can look at them today. And in fact, please provide feedback. So, okay, here are some core concepts for some of the interop specifications. First, cross-chain reads we're going to talk about, chain dependencies, and the proof system for this thing. So this is essentially how we go from the cross-chain messaging as a high-level concept that I was just talking about into some more, tangible details. Okay, for cross-chain reads, what is the specific, what are we reading? Well, we're reading events. This is events from other chains. We can now read those events. Why events? Well, there are already a lot of tooling that exists around events. Pretty simple. Also, events are extremely easy to look up and also extremely easy to expire. They all come in a kind of orderly list. We can take the latest day of events or week of events or month of events and then expire the rest. So this is, a nice property versus the infinite state growth. And so then once we can read the events, so I'm on a chain, I can now read the events of another chain. Once we have that primitive, then we can build out things like message passing on top of that to not only read an event, but do things like replay protection or general replayability, nice features that you would want on a message passing protocol. So think of it as like UDP and TCP built on top. So you build out the message passing, the TCP style thing on top of that. And we've got the proof system. I'll just note here, right, we've got to make it so that the proof system supports this same block event reading, which is very nice, right? Eventually we'll get to atomic cross-chain transactions, but it'll take some time, and the sequencers are not going to support that for quite some time. So that's just cross-chain reads, pretty simple, not too bad. Cross-chain dependencies or chain dependencies. What are these dependent chains? Well, chains can read at low latency these events from other chains that are in their dependency set. So what does this mean? What is a dependency set? We're kind of like adding a new primitive, and it's a kind of cool thing, adding a new primitive to a chain, to what a chain is, that it can depend on other chains. So what are these dependencies? They're unidirectional. That means that I can spin up a chain that's, that reads from multiple different chains. Maybe I read from 30 different chains. It's not a problem, very easy. But it may also be hard because now I have to make sure that I run 30 different chains nodes, like all these kinds of things. Also, dependencies are, of course, transitive. Chain A, chain B, and chain C. If chain B depends on chain C, then if chain A depends on chain B, then chain A will also depend on chain C, right? You kind of like inherit all of the dependencies. And of course, two-way dependencies, that's how you kind of enable asset bridging. So if chain A depends on chain B depends on chain A, then you can bridge assets between them. And so you can form like little like either clusters or all of these things for low latency, like really low latency. Now, to kind of go into that a tiny bit, basically the high latency bridging, that's achievable with normal proofs for reasons that I won't go into in this moment. We can get even lower latency, for example, like same block messages, if we have this kind of abstraction of chain dependencies. All right, so yes, expect a core cluster of two-way dependent chains, nice, and importantly, syncing a chain. I'm syncing, chain A. It requires a client for all of the dependent chains or a light client for all of the dependent chains. So this is actually how you can kind of get into things like secure light clients with either off-chain fault proofs or zero-knowledge proofs. So you can have guarantees about your cross-chain messaging. And this is actually how you kind of, by the way, oh yeah, another concept. It's just in general, people are always like, oh, it's the OP stack. It's all about optimistic rollups. Yes, we like optimism as a concept high level, but it's not just about optimistic rollups. We have to use ZK. And so this is a really clean way for us to integrate it in. It's used to secure the light clients for these dependent chains. And as we scale up, we can secure more. All right, now let's talk about the proof system. Amazing. So proof stack, pretty much the same. We built out the system to be pretty modular so that we only need to change, for example, like the OP program, the proof program, to support this kind of new structure and new way to read messages from each other. So, you kind of like think of it, the change in the program is you split it up into two steps. First, right now we only have this like execute step, but what we can do is we can do the execute step first for all of the blocks, and then we have a resolve step that just resolves all of those cross-chain messages. Relatively simple. And so this is the nice little modification. So the way that it works, right, we've got two chains, and we've got two messages, one in each chain. We have a little resolve dependency step, check the dependencies, and move forward. So now we have done three things. We can read events from OP chains, get low latency reads for, like fully atomic for the chain dependencies, and we can prove the authenticity of all this stuff with a nice modified proof system. Did I say a proof system, a proof stack? Well, in fact, we deployed on testnet the fault proof system, which you can play with today. In fact, I have been really enjoying it. There's a little secret. If you go on Etherscan and you kind of like dig around, you can submit, it's fully permissionless. So you can submit invalid proposals, no problem. And through the Etherscan UI is very easy. And then you can watch yourself in real time get challenged. And then you can attempt to challenge back. Of course, be careful, you'll lose your bonds, unless you found a bug, which would be sick. So anyway, I recommend trying it out. I was like, I could have done a live demo, but I don't have my laptop. But yeah, I just keep getting challenged. It's rough. All right, well, we've got 5 minutes. I'm going to transition back. You know, we had a great time with the hamster's very happy. And then now I'll transition back, switching gears back to the presentation. We've got infinite chains. Now we've got chain message passing. And so we're going to do the rest of this presentation in 1 minute, so I still have a couple minutes for questions. Well, what are we going to do? The messages are asynchronous, so we introduce decentralized shared sequencing. Boom, and now we just get to watch and just feel the atomicity coming up. Oh my gosh, look at that atomicity through shared sequencing and all these things that are synchronized. Okay, and then the last concept is data availability. Remember I mentioned it before. We've got infinite chains. We've got a data bottleneck. What am I going to do? Well, EIP 444 and Plasma for AltDA, so we can standardize how AltDA gets plugged in, and infinite chains meet infinite data. And there's a catch, of course. You know, AltDA isn't as secure as normal data, but we've got data availability challenges. And yes, there's no fisherman's dilemma problem here, y'all. Don't worry, don't worry. We know our classic Vitalik posts. Roll-ups, plasmas, you know, pretty chill. So yeah, we've got the full thing. We've got infinite chains. We've got cross-chain messaging. We've got synchronization between them and infinite data. We got the superchain that's just coming. It's so close. And there's congestion. Pow! We knocked it out. Look at that. We achieved our goals. And to infinity and beyond, you know, we're going to create this beautiful open source ecosystem and summon Ether's Phoenix to fund public goods and coordinate the world around an open source and decentralized internet that benefits human beings, because the impending superintelligence will kill us otherwise. So save the race and scale Ethereum. Thank you very much. We got like a couple minutes for questions. Any questions, y'all?
Yeah, so the question basically about the finalization time of optimism chain. So the block finalization the challenge takes up to 7 days, right? So how we can trust the proof coming from one chain to another chain, verifying it, if it can have invalid state truth, because the fraud proof didn't come yet to Ethereum main chain, so it can have invalid state. So how that kind of brings the fast transaction cross-chain if the finalization time is 7 days.
Nice. So this is kind of where the chain dependency stuff comes in. I feel like to think of it as there are like two things here that happen. There's subjective finality and objective finality. It takes 7 days to get to kind of quote unquote objective finality, where the fault proof finishes and everyone knows what the state is going to be. But for that 7 days, it is possible to predict what the chain state is going to be. And so you can, similar to how the sequencer can give a kind of optimistic confirmation of a transaction before it lands on L1, similarly, we can basically predict what the chain state is going to be before the fault proof resolves. Now, notably, it's important that the proof system does resolve as we would expect. And so if you do, have this property where you are dependent on a chain and you wait a full 7 days for it to kind of come to full objective finality, then you need to make sure that neither one of those chains finalizes incorrectly. So this is why the chains become, in some sense, intertwined. But this is actually more of a sliding scale than we normally think, because we could, for example, have a multi-proof where we have a zero-knowledge proof that we get in low latency, but then a fault proof which we get in high latency, and we've only resolved the zero-knowledge proof to kind of get the low latency message passing, but we haven't had the fault proof resolved. And so there's actually like weird hybrid solutions that I could get into, but it's a great question, and this is like, my best attempt at a 30-second response. Any more questions? Yes.
Is it possible to transfer NFT between superchains?
Nice. Yes, with cross-chain messaging, that's absolutely possible. The whole point is that it's really about authenticating secure messages, and those messages can be, for example, I burn an NFT here, and please mint it over here. And then on the destination chain, it mints because it verified the burn event.
Thank you.
We got the questions coming. Let's go. The juices are flowing.
Can the proof system for the multi-chain between the LP stack also work for like other optimistic graph like Arbitron? So this proof system can be like IBC for Ethereum, or is special for the LP stack?
Nice. So, okay, I'll tell you what we're hoping to do is create a kind of like universal interoperability protocol that allows you to kind of program with all of the different interop, either all the different chains that you're using or the different kind of like proof systems that you might use to communicate between those chains. But there are going to be differences in that, like, for example, as an application developer, it's going to be a lot easier to, for example, deploy my application to the same kind of block space versus supporting many different kinds of block space. But it is 100% a goal to like zoom out to a sufficient angle where we can kind of cover all of the different types of chains, types of proof systems, and third-party bridges and all this kind of stuff.
Okay.
One last question.
Okay.
You had your hand up first. I want to make sure that we get that question. I'm so sorry.
So since the superchain will require like a single agreed upon standardization, like, do you think we might see chains previously a part of the superchain that disagree and then fork to create their own standardization versions, and how might that be handled in the future?
Nice. So this is also related to the last question around like, does interoperability work for non-homogeneous chains? So there are two things. One, of course, we're going to make sure that migration paths are as painless as possible. There are some fundamental issues with migrating. Like, it's not always going to be easy depending on what change you made. So that is one thing. So going from non-standard to standard, make sure that happens. However, the second thing is if you are, for whatever reason, stuck on a non-standard chain, we can't leave you out. We got to make sure that there's at least some interoperability features that you can benefit from. Now, notably, it may be the case that things like, for example, super low latency message passing don't work in that context, but you get, some level of low latency just a little bit higher. Things like that. And of course, we'll have to solve it later on. Cool.
Thank you. Thank you for the wonderful presentation, Karl. Let's give it a round.